Okay, so it's been a little while since we learned a new lesson because we did the cumulative review and then we had Christmas break. But the very last thing we talked about were exponents. And the next thing we're going to talk about in the second half of Unit 2 is logarithms. I love logarithms. Most of the Algebra 2 teachers I don't think do. So you might get a new perspective about logarithms from someone who actually enjoys logarithms. But before we get into logarithms, we're going to review some rules and ideas about exponents. And you don't have to write this down unless you just want to. But what is 2 to the third?
6.
It's okay. What about 2 to the second?
4.
And 2 to the first? Okay. So 2 to the 0 is weird. So it might not be something that you just remember like 2 to the second or 2 to the first. So most mathematical concepts were developed from patterns. So what is the pattern on the left? Like what's happening on the left?
It's going down.
Right, the exponent is decreasing by 1. What is the pattern on the right? Half. You're taking half. So or dividing by 2. So if I take half again, what would I get? 1. So that is why anything except 0 to the 0 power is 1. Okay, let's continue that pattern. So if we're continuing that pattern, what's 2 to the negative 1? 1/2. 2 to the negative 2, 1/4. 1/8. All right, so I'm sure at some point you learned that a negative exponent means a reciprocal, or a negative exponent means you put it in the denominator and then raise it to the power, which is great. But it also helps to know why. And the why is just the patterns. You're continuing the pattern by dividing by 2, dividing by the base. Okay, another thing I know you learned at some point is what exponent means square root. Does anybody remember? Okay, so let's figure it out. So if you take the square root of 2 and you multiply it by the square root of 2, what do you get? 2. You just get 2. Or 2 to the first power. So whatever power means to take a square root, I'm having a hard time articulating that for some reason. You should be able to do 2 to that power times 2 to that same power and get 1. So whenever the bases are the same, what do you do to those powers? You add them, yes. So whatever that is, you would add something to itself and get 1. So what is it? What can you add to itself and get 1? 0.5 or 1/2. So an exponent of 1/2, sorry, it's hard to squeeze it in there, means the square root. So anytime you have a fractional exponent, it means some kind of root. 1/2 means square root. Okay, so let's think about some other roots. So if I take the cube root of 2 and I cube it, what do you get? 2. The cube gets rid of the cube root. They're inverse operations. Okay, so if the cube root has a power, 2 to that power raised to the third means 2 to the first. So what is the rule for a power raised to a power? What do you do with those two? Multiply them. So I need to be able to multiply whatever that power is by 3 and get 1. So what would that power be? 1/3. So raising to the 1/3 means the cube root. So I know you've learned that, but I don't think you remember it. And you might not remember it even after I show you why it's true. But it does help sometimes to know why 0 or 2 to the 0 is 1, and why 2 to the 1/2 means the square root. So hopefully you'll remember, because it's going to come up a lot. Okay, so let's go back to the notes. So every mathematical operation has exactly one inverse operation. And so what is the inverse operation of addition? Subtraction. What about multiplication? Division. What about cubing? Cube root. What about exponentiation? That's a fun way to say. Yes. A logarithm is the inverse operation of exponentiation. So eventually, it's going to be a little while, but eventually we're going to solve exponential equations where the exponent is the variable you want. And the way that you solve it is to use logarithms because that's the inverse operation. Okay. And so one thing we're going to do is write these in different forms. So someone earlier, when I was expecting someone to say 1/2, they said 0.5, which was 100% right because 0.5 is just another way to write 1/2. And so logarithms is just another way to write an exponential equation. So we can also write equations in exponential or logarithmic forms. Okay. Now, a lot of people in Algebra 2, and when I taught Algebra 2, I 100% did this. To go back and forth the forms, they do the loop. Do you guys remember the loop? Okay. So it's a nice way to help remember how you go back and forth. So if I have b to the a equals c, and I want to write it in logarithmic form, I start with log, and then I just go around the loop. So I start with the b, I loop over to the c, and then it equals the a. Right? And then you can do the loop the other way also. If you have it in logarithmic form and you want to write it in exponential form, you start with the base, the b, you loop over to the a equals the c. So a lot of people remember that from Algebra 2. That's really good. Just a note that helps me also, another thing that helps me remember how to write these differently is that a logarithm always equals an exponent. All right, so the base is kind of obvious. The big base, is the base of the exponent or it's the base of the logarithm. And then if you can remember that the logarithm is always equal to the exponent, you know where to put that. So then the only other thing that there is goes in the other space. In a logarithm, that c is called the argument. So sometimes I'll talk about the argument. Okay, and then there's a notation. I'm going to actually add another notation. There's two kind of special logarithms. One of them is called the common log, and it's whenever the base is 10. And whenever the base is 10, you a lot of times write it without the base. So if you just see log of 3, that means log base 10 of 3. Do you guys know what the other special logarithm is? Yes. Log base e. Do you know what that's called? It's okay, that's good. It's a natural log. Now you never write it log base e. E is Euler's number. Euler is the red guy back there. And whenever it's log base e, you write it, do you guys remember? Ellen, good. Nobody remembered last period. Now it's not I. I see tons of people call it IN. It is not an I, it is an L. You can do uppercase if you want to. Why do you guys think it's LN instead of NL for a natural log? I think it's because Euler didn't speak English. And just about every other language I know, which is not, I don't know a lot of languages, but they don't do adjective, noun, they do noun, adjective. So I think it's like log, natural, or whatever. That's what I think. I don't know. That's not proven fact. Okay, so on example 1 and 2, we're going to just write it in the other form. So we're going to take exponential and write it as logarithmic. And so when you're writing in logarithmic form, you start with the word log. And then you can draw the loop if you want the loop. It's fine. But whatever the big base is becomes the little base. 9 is the argument, and the logarithm always equals the exponent. Right, and then for B, since it's base 10, you have options. I usually, if it's base 10, I just don't write the base. And then of y equals x. All right, so you guys try C and D on your own if you haven't already. D is a little tricky. Let me switch things up. All right, so just be careful on D that you don't write log base E, that you just write it as natural log of y is 3x. Okay, and then we're going to do the opposite. So this one, we are going to write an exponential. So the base is, you can do the loop if you want to, but the base is 7, raised to the second is x. Right, and then on C, no base means what base? 10. All right, what questions do you guys have so far? Good. Okay, and now one thing that you guys, I'm not sure if you did a lot of this in Algebra 2 because you use your calculator a whole lot in that class, and you guys obviously know we don't. So we're going to do all of these A through H without a calculator, just using our brain and the rules for exponents to figure out the logarithm. And so when you're doing this, when you're evaluating logarithms, you're figuring out the exponent. And so if you're doing one like A, you would ask yourself 2 to what power gives you 8? What would you answer yourself? 3rd, good. I thought you were holding up 2 fingers.
No, I have to keep my
All right, and then for B, you would ask yourself 5. So what power gives you 25? Yep. Now some of these is stuff you might not have memorized, so it might take you a second to figure it out. What do you guys think about C? 5, good. All right, and what would you ask yourself on D?
10.
What would you ask yourself then? I gave it away. 10. So what power gives you 100? Yeah. So those powers of 10, 100 is easy because everyone knows that 10 squared is 100. But for the bigger values, then it's just, if it's a 1, it's just going to be however many zeros are after the 1. That should be the power. Okay, next row gets a lot more challenging. So on E, you're going to ask yourself 16, so what power gives you 4? Negative 2 would turn into a fraction. 1/2. 1/2 is going to be the square root. All right, and then for F, 3, to what power gives you 1? Yeah. All right, sometimes these obvious ones, I have a crazy smart kid in my second period, and the obvious ones threw him for a loop. But 10 to what power gives you 10? Yeah. All right, and then 6 to what power gives you 1/36? It's a negative 2, yeah. So the negative turns it to a fraction, and then squaring 6 gives you the 36. Okay, these calculator ones, I don't want us to spend a lot of time on it, so if you don't have a calculator, it's fine unless you're really close. You can try. Okay, so whenever it's log without a base, common log base 10, then you're just going to use the log button in the calculator that's right beside 7. super easy to use. Now, the reason you would need to use a calculator, if you asked yourself 10 to what power gives you 9, that's not something you can figure out in your head. Can you figure out about what it is? Would it be bigger than 1 or less than 1? It'd be less than 1, a little bit less than 1. Because 10 to the first would give you 10. Okay, and then we want 10 to what power gives you 6,125. Can you guess what two numbers it would be in between?
1 and 2.
1 and 2 would be between 10 and 100.
Or 2 and 3.
2 and 3 would be 100 and 1,000. It's 3 and 4.
I was getting there.
It's okay. So 10 to the third is going to be 1,000, and because it's a 1 with 3 zeros, and then 10 to the fourth would be 10,000. So it's going to be in between those two. It's okay. I'm just trying to get you guys to think about something that's really easy to do in the calculator. So we were right, between 3 and 4. Okay, 2 to what power gives you 10? Do you know what two numbers it would be in between?
3 and 4.
Yes, because 10 is between 8 and 16. It should be between 3 and 4. What should it be closer to, do you think?
2. Or
3, yeah, good. Okay, this one, we can't just do log in the calculator because it's log base 2. Do you guys remember how to get log base? It's alpha window. So if there's something you're like, I know it's somewhere in my calculator, I'm not sure where, it's probably alpha window. So it's log base, and then you just make it the base of 2, and the argument 10, and there it is. All right, and then log base 7 of 135. So 7 squared is 49. 7 cubed is 343. One I always have to think about. So I know it's going to be between those two. All right. Okay, and then I like how Brian Passwater, like that was all review. I think it probably felt, you might not remember everything perfectly, but you know you've done it before. But he also has thrown in something completely new, which is good. It's good to learn something new every day, I think. But there is a purpose of logarithms in statistics. And so they can take exponential data and kind of straighten it out. That makes it easier to do statistical analysis with. So what we have here on the left and the right is the population of English Americans in the United States between 1620 and 1820. And so we're looking at this one. These values are all so close together. It's kind of hard to tell like what's even happening. It looks like it's just flat. And so what this graph is this axis is not going, this one's going by 1,000,000. This one is increasing as a power of 10. So this is 10, this is 100, this is 1,000, this is 10,000. And so it's not a equal amount that is increasing by like the first one. And so you can see it kind of lines up the points and you can do a statistical analysis with it better. All right, so we're not doing statistical analysis with this. What we're going to do today is just plot some points when the vertical axis is called logarithmically scaled. Okay, and so we're going to graph these 3 points. And so this up here would be a 1 with 7 zeros. All right, and then if we had another equally spaced point, it would be 100 million, million, sorry. All right, so we're going to graph these 2 points, 17 million, 31 million, and 50 million, in between 10 million and 100 million. What should 17 million be a little bit closer to? or a lot closer to actually. The 10 million. So this is not easy to do, and it's okay. We're just gonna estimate about where it is. It's hard for me to see it without lines. So 1840 is 220 years since 1620. All right, the next one should be just a little bit higher. And the next one should be just a little bit higher. And we're going to come back to this. We're going to do a whole lesson on these types of graphs, so don't get too stressed about this today. But one thing that I want you to jot down, and again, we will come back to it, but in this space we have exponential characteristics appear to be linear. When the y-axis is logarithmically scaled. And I cannot see all the multiple choice questions that you'll take, but I can almost guarantee there's going to be a graph that's logarithmically scaled, and it'll tell you that. And then it'll say what type of graph is this. And it's going to look linear, but the answer is going to be exponential. So when an exponential graph or function is graphed on a logarithmically scaled y-axis, it's going to look like a line. I'll have to tell you that again. You're not going to remember it. It's okay. Another thing they're going to do is give you these kind of graphs, which are a lot easier to graph with. And they're going to ask you to pick out the ordered pair of a point that's graphed. So let's talk about how this works. If it is logarithmically scaled on the y-axis, there's no way to graph a y of 0. It doesn't exist because 10 to nothing ever gives you 0. So we start with 1. And so this is 1. This next line is 2, and then 3, and then 4. And then they do get skinnier and skinnier and skinnier. I can't fit all the numbers in there, but it goes 5, 6, 7, 8, 9, 10. So here's 10. What do you think this one is? 20. So then it's 20, 30, 40, 50, 60, 70, 80, 90, 100. And then once we get to 100, it's 200, 300, 400, all the way to 1,000. Pretty cool. Okay, so once you kind of get that idea, it's not too hard to graph these points. So 120 is just going to be this point right here. 300. 2. All right, so 15 isn't an actual line. But I know 15 should fall right in between 10 and 20. And same thing with 350. So 350 isn't a line, but I know it's going to be in between 300 and 400. All right, what questions do you guys have?